Throughout this course, we will have many opportunities to work with and create models based on a given data set. The three particularly important examples that we've gone over so far in class are linear, quadratic, and exponential models. Since these three models occur frequently in the real world, there's a larger emphasis on them in this class. On the AP exam, you are expected to determine which model is most appropriate to a given data set. So if we were looking at maybe a graph, and you see the three graphs on this page, it's pretty obvious to you visually that the one that goes in essentially a straight line would be linear. Yes? So we can look at this one and say, linears go in straight lines. The things we know about these things that go in a straight line is they have a relatively constant rate of change. And if we were trying to describe it properly, to say why it is linear, we would say that over equal length input value intervals, the output values have a constant rate of change. That's things we know, right? Those words sound familiar? You could also maybe look at this quadratic model where the values go down and come back up. Since they go down and come back up, they follow a quadratic regression. This also makes sense if it goes up and comes back down. We would say that quadratic models are used when the rates of changes are increasing and decreasing at a relatively constant rate. So that's a change in the rate of change. We would write as our explanation that over equal length input value intervals, the output values have a constant change in the rate of change. Those are words we've heard before, yes? Maybe. The third type of function we've studied so far is the kind of function that has an initial value either above or below the x-axis and then increases and decreases proportionally, meaning by multiplication. So it like whooshes up, or in the other case, whooshes down to get close to the horizontal asymptote. That would be an exponential. We would say that the output values are roughly proportional, or we'd say that over equal length input value intervals, the output values change proportionately. Those are the sort of responses we've given so far in this class to determine why maybe a table would represent linear, quadratic, or exponential. But so far in this class, I've given you nice, neat patterns where it's obviously clear that's the kind of function to be used. If we actually look for a second at these tables, they're decimals, panic. Does this actually have a constant rate of change? This would be plus 1.6. Is this plus 1.6? No, so if we were trying to do this from a table, we wouldn't be able to use the language we had been learning so far to be able to validate that we're using the right kind of function. Same thing for quadratic. If we actually found the second difference of this table, the change in the rate of change, it wouldn't necessarily be the same because I've given you nice, pretty numbers so far that have made that obviously clear. Same thing for exponential. We wouldn't be able to multiply by some number for each output because I haven't picked nice, pretty numbers for you. But in the real world, we're going to take these sort of datas and write what's called lines of best fit. Do y'all remember that vocabulary from Algebra 1? That's the best we can do to connect all the dots. Do you notice that those dots are not all actually connected? There's a little bit of error above and a little bit of error below each of the values. We're going to explore today why we are able to use these functions anyways to write the model that represents this data. If you flip to the next page, please. We're using what are called residuals. When we create a model, When we create a model, we can use our model to predict the values. If you remember in the calculator, I asked a lot of you this question at the door. When we're predicting the future, what do you type in the calculator? On the home screen? A lot of people I had type it on alpha something. How about a Y1, yes? With the number plugged in? When we're using this to predict values for the dependent value or the output, it's a predicted value. This is why I keep calling it predicting the future. We're using the regression model that we created to predict what's going to happen based on that model. But if we actually have real data, we can use what's called a residual to find the error in our predicted value by doing the actual output value minus the predicted output value. That's called a residual. You can think of a residual kind of like the error in your model. The residual is kind of like the error. So we'll take the actual output value and subtract the predicted output value. If you go online and are looking things up for help on residuals, you will see a formula that says this, y minus y hat, which is literally a y with like a hat on it. That is the formula used for actual output value and predicted output value, y minus y hat. And I think that's the silliest name for a symbol. And as a mathematician, it makes me laugh every time. It's literally called a y hat. Okay. Let's just jump into it so you can see how we might use a residual in the future. Example 1 says the weight of newborn babies can be modeled by a linear function for the first 4 months after birth, meaning they're gaining weight. Yes, for 4 months, linearly, babies gain weight. The selected values for the weight, W of t, in kilograms of a particular newborn baby are given in the table on the right, where t represents the number of months since birth. Use the regression capabilities on your calculator to find a linear model. Let's highlight the word linear model of the form a plus bt. A plus bt is option 8 on your calculate screen. It's the linear regression that has a plus bt. It literally tells you what form it wants it in for the weight of this baby t months after birth. So everybody has their calculator, yes? We went over these steps previously, so I'm not going to walk back to my computer and do them underneath the screen. Everybody grab their calculator, and let's put this table into stat edit. We go stat, we go edit, 0, 1, 2, 3, 4. In L2, 3.2, 4.2, 5.1, I already typoed something, 5.8, and 6.4. After we do this, meaning having the inputs in L1 and the outputs in L2, what do I press? Stat calc. And which option? 8. Oh, 0 is for exponential. What kind of function does it tell us this is? Linear. You have 2 options for linear, so you make sure you use the correct one. This one is the version 8. Once we've selected option 8, we scroll down to where it says store regression equation, and what do we type there? We put an alpha, or sorry, a y1 there by pressing alpha y equals, what? No, alpha trace enter, so sorry. And then we calculate. All of that to say we should have an equation that is written like this. W of t equal to 3.34 plus 0.8 t. I'm correct. I'm using the formula that's written on the calculator screen and making sure I plug in the a and b values in the appropriate place.
So after we type all of them in the thing, what do we do?
Stat calculate.
Do we always gotta put that 0?
No. I just do it so it makes sure that it doesn't look like I just have a random, like they don't accidentally think that's 8 because my dot is too light or something. Part B says, use the model found in Part A to predict the weight of this baby 2.5 months after birth. Because we have the Y1 already saved in our calculator, to find the weight when the months is 2.5, we're going to do in our home screen, Y1 parentheses 2.5. And yes, it should give us, like Shane said, 5.34 kilograms. This, my friends, is the predicted value. So it's a great question. This is just a prediction. If we read part C, it says the actual weight of this baby 2.5 months after birth was 5.5 kilograms. This is the actual. The question says, what was the residual or error for this weight prediction? Did our model underestimate or overestimate the weight of this baby 2.5 months? Okay, wait, let's do numbers to make sure. If we're finding the residual is always the actual minus the predicted. The actual we were given was 5.5. The one that we predicted was 5.34. So if in your calculator you do 5.5 minus 5.34, what do you get? 0.16. That's the error. That's the residual. And then, if you guys already saw this, did our value underestimate or overestimate?
Under, right?
Yes, so our model, the one we predicted, our model underestimated the weight by 0.16. Because our residual or our error was off, our model was off by 0.16 kilograms. When we did part D, which you did on your own, it says use the model found in part A to predict the weight of the baby 4 months after birth. Hopefully in your calculator to find W of 4, you did Y1 parentheses 4 close parentheses. Did you get 6.54 kilograms?
Yes.
Now that's my predicted, so that's Y hat, right? Part E says, what is the residual for this weight prediction? And a lot of you fell for my trick, haha. It didn't tell you the weight prediction in this question. Where did you have to go find the weight prediction? In the table. In the table, it tells me that at 4 months, this baby actually weighed 6.4. So we are going to use this information here, as the actual value. So when we make the residual, which is residual equal to y minus y hat, we would do 6.4 minus 6.54, and we'd get the residual is negative 0.14. Do you agree? So does that mean that our model over or underestimated?
Under. Where are you getting 6.4 from?
Miss, what do you mean?
Where are you getting negative from?
Okay, let me address both of those questions. Where am I getting 6.4 from? Again, in the table, it told me at 4 months old.
And then when you plug in, okay.
Correct. And then you said, how did I get negative? 6.4 minus 6.54? 6.54 is larger. No, because remember, it's the actual minus predicted. The actual value was 6.4. Our predicted value was 6.54.
Oh, she said, what is that thing on top of Y?
Hat. Y hat is how you pronounce it, but it's predicted.
So that means predicted.
That means predicted. So wait, I forgot what you guys said here. Our model does what? Under or overestimate?
Under.
6.54 is larger than an actual weight, so our model overestimates.
Nice job.
Miss, what is that thing on top of the wall?
It's a hat. I love that some of you got confused when I asked overestimate, because I'm pretty sure you're thinking to yourself, well, that's a negative number, so it must be under. Is that what your brain thought? That's a great thought, but here's why that this is wrong. In a residual graph, because we're finding error, your predicted value, if it's more than the actual value, you'll end up with a negative number as an overestimate, and vice versa, which makes the next part of this graph, or next part of these notes, when we put it on a graph, a little confusing. We can then take the error that we get from multiple predictions and create what's called a residual plot. And we can use the residual plot to check the appropriateness of a model. Kind of like at the beginning of this lesson, when I said those numbers won't exactly fit on the line, but their error would be random because we've done our best to fit the line on the linear curve or the quadratic curve or the exponential curve. So a residual plot shows all of the residuals for a set of data and can be used to determine if a model is appropriate. When we're looking if a model is appropriate, this is bolded, but we're also going to highlight. If a model for a given set of data is appropriate, the residual plot that we're going to plot should appear without a pattern. If there is a pattern in the residual plot, then that type of regression is not appropriate for the data. Additionally, when we see our data points that we got on the other side of this paper, for week 2.5, we got that our residual was 0.16. And we said that that was an underestimation. When we did the other problem and we did 5 months, we got that our residual was negative 0.14. And we said that that was an overestimation. So what kind of conclusion can you draw about data points on a residual plot?
Negatives will always be over.
Negative outputs for a residual plot will be overestimates.
So it's backwards.
And correct, it's backwards. The things up top are underestimates. The things on the bottom are overestimates, which is weird. Because of the error, because you're doing actual minus the predicted. So if your prediction is too much, you're getting a negative number. If your prediction is too little, you're getting a positive number. But let's see the kinds of questions I'm going to ask you, because we're not necessarily going to be plotting a bunch of residual data, because that's a statistical thing, and if you take stats, we'll do it, but not in this class. Example 2 says, an exponential regression was used to model a data set. The residual plot for the exponential regression is shown on the right. What is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? Here's what you need to ask yourself. Is there any pattern to these dots? Or is it pretty random? It's pretty random, right? That means that this is appropriate. Our conclusion is this. Because we tried to use an exponential model to do this, an exponential model is appropriate because the residual plot shows no clear pattern. In example 3, it says, a group of AP Pre-Cal students used a set of data to create linear, this is the linear, quadratic, this one's the quadratic, and exponential regression models. They were trying to figure out which one they should actually use because it's unclear from the table of data they have whether it changes, the outputs change linearly, the outputs have a constant change in the rate of change, or the outputs change proportionally. After creating these 3 residual models, the students had the residual plot, and based on the plots, we need to figure out which student made the most appropriate model. So if you look at the regression that was linear, is there a pattern to this?
Yes.
Yeah, so is that appropriate?
Yeah.
No,
Oh, it's opposite.
it's opposite. You don't want a pattern. Does the quadratic have a clear pattern?
Yes.
So no good. Does the exponential have a clear pattern? No. Which means that we want to use the exponential. This one has a pattern. This one has a pattern. This one has no pattern. So the only option that's appropriate is the exponential data. So we would write the conclusion that based on the residual plots, an exponential model is most appropriate.
What is that based on?
Residual.
Do we have to write them?
Nah.
No, I mean, like, on the
These will all come from multiple choice questions on the AP exam, but for me, yes, I want you to be able to write mathematical conclusions. Example 4 says, students in a pre-cal class measured each student's height and arm span in centimeters and calculated a linear regression. Ooh, what kind of regression?
Linear.
Linear. Hey, random question. Would that be option 4 or option 8 in the calculator?
It's both, actually.
Well, linear is both, but based on the way that it's written, a plus bx, is that 4 or 8? 8, good. Okay, with the heights as the input values and arm spans as the output values. The given residual plot has point P at the coordinates 175, 23.4. What does point P indicate in the context? If we were looking at this on a residual plot, and I'm going to zoom in over here because I can't write small enough for this. On a residual plot, you have 175 as the input, and you have 23.4 as the output. So does that mean that based on point P, because it's above the x-axis, the student with a height of 175 centimeters, the model blank under or overestimates the actual arm span?
Under, 'cause it's positive, right?
Correct. Underestimate because that dot is above the x-axis, which meant the actual data was more than the predicted data. So we underestimate the option. The reason that we learn about the residuals is because when we're trying to make a choice on what kind of function is appropriate and the data isn't perfect, we need a way to run an experiment, a residual, and see which which model is most appropriate. And that's why we do this the way that we do this. Your job in this class is not necessarily to make the residuals, not the plots at least. You want me to be asking you to calculate a residual, because residual plots is a statistical thing that you would do in stats classes. But you need to be able to read them and know if you have an overestimate or underestimate and when a graph is appropriate or not. Sound good?